In this video, we're going to start to look at the behavior of explicitly defined sequences as my n, in terms of term number, starts to approach infinity. Now, sequences, we're treating them like functions. However, all we can do is we can put in integers for n, and where we work our way, and we try to analyze those as we would with regular functions. Now, we're going to use Desmos here to help us look and analyze these sequences. As you progress forward, a lot of time is devoted to studying sequences and series in Calculus 2. But to do so, we're going to open up a Desmos graph, and we're going to have we're going to type things in here a certain way. And this link here provided, it's already typed in, where all we're going to do is we're going to adjust our explicit formula, and we're going to look at the behavior in terms of what's happening to a function as I work my way and increase the index number for certain terms. So we're going to start here with our first sequence, which is the sequence 1 over n. And I want to look and say, what is happening to the term value as I start from 1 and proceed towards infinity for n value. And so here we have, when it typed in, and so the a of x is really the a of n. So that 1 over n I'm going to type in as 1 over x. And so that second block here is our explicit equation. Now, I want to look at what is the term values as I start to approach infinity. Well, I'm just going to kind of drag a slider here in terms of work my way to the 100th term. I'm going to see the overall behavior. So the first term is 1, 1. So if I put in 1 for n, I get a term value of 1. So I'm really looking at the y values. As I work my way to the right, now my n's here can only increase by 1, so I need to make sure that step is 1 unit in terms of what it can plot. And then I'm going to work my way to the right, and it should be plotting points. I'm just going to go drag all the way over here to 100. Now what we're looking at is, well, what's happening to the overall value of the term as n increases all the way towards 100. Now this would continue on forever, and we're looking at the overall value, and it's getting very, very, very close to 0. And I see that the 100th term is at 0.1, and it's starting to level out and slowly working its way to 0. And so that is what is happening there for this one. And so graphically what we saw is our terms were heading closer to the x-axis. Now the description of what is happening as n was approaching infinity, 1 over n was approaching a value of 0. And what we can do is we can write this using a limit notation. Now it's because it says using limit. So the limit notation is basically describing what happens as n increases without bound. So we would say the limit as n approaches infinity. And I'm going to let a of n be our explicit form. So I'm going to say a of n. Of a of n, it was heading towards 0, so we're going to say that's what our limit equaled right there. So that sequence was approaching a number of 0. Now let's work our way, and let's go look at a second equation. So we have the explicitly defined function here of 2 plus 1 over n. And we want to look and say, what is the overall behavior as we start increasing the size of n towards infinity? So let's go back to Desmos to do that. All right, so I had to move my graph around a little bit so I could see it. So we start with, when n is 1, we start with the value of 3. And we're going to work our way and watch the overall behavior in terms of the values as I increase the size of n for my certain term. So by the time I work my way to like the 6th term, my 6th term has a value of 2.1666 repeating, and it's going to round it for me. And so I'm just going to keep going until I get about to the 100th term. So as I work my way to the 100th term, notice how we're starting to flatten out here. And it's getting very, very, very close to a value of 2. So we can generalize what we're seeing here on the graph and say, hey, as we continued on forward, if we did this forever, we'd be approaching a value of 2 in terms of our sequence value. So roughly what we saw in Desmos was as we worked our way and we continued to increase the size of n, we started to approach a value of 2. And so our description as n approached infinity, 2n plus 1 over n approached a value of 2. And we're going to write this using limit notation. So we'll say the limit as n approaches infinity, so our index number approaches infinity, our explicit formula, an, is approaching a value of 2, so we'll say equals 2, so there's our limit there. All right, and we're going to do the same thing again. So our next equation we want to look at with Desmos is n squared plus 1 over 2n. So we'll go into Desmos and look at the graph of that sequence. All right, so graphically, I'm just going to drag the slider and we look and we have our first term here is at a value of 1. And I'm going to start increasing the size of n and we're going to look at what's happening. So as I start to increase the size of n, it just keeps going up. I'm not even at the 100th term yet. And its value continues to go higher and higher and higher and higher. And we're looking and we're saying, well, does it approach, is it getting closer to a particular number? It looks to me like it just continues to go straight up. And so let's illustrate what is happening. So as on Desmos, we're a rough sketch. As we increase the size of n, we just kept getting larger and larger and larger term value. So our description as n approaches infinity, n squared plus 1 over 2n, continued to increase forever. So we're going to say it was also approaching infinity. So if I write this as a limit, so the limit describing the behavior of our sequence as n approaches infinity, our explicit formula's output was also approaching infinity. So I'd say equals infinity here. So that would be my limit. And then we have one more we want to do. So we want to look at the sine function, the sine of n pi over 6 as we go from 1 to infinity. All right, and so we adjusted our equation here in Desmos to account for a new explicit formula. Let's start dragging our slider, and let's see what is going on with our term values here. So my first term, sine has a value, in this case of 0.5, and then I keep dragging on to see what's happening, and notice how it's bouncing up and down as I continue on to get to my 100th term, and I don't really see it narrowing in on a certain value. And so since it doesn't narrow in on a certain value, or it doesn't continue to increase or decrease forever, we can't actually determine what it is approaching. And so if I have this function and it's constantly going in between two values, we can't describe what its limit's doing. So what we would have to say in this case is the limit as n approaches infinity for a of n, we would have to say it's non-existent or D&E because we can't illustrate with a symbol of positive, negative, infinity, or even a number in terms of what the graph's approaching because it's constantly oscillating in between two fixed numbers, -1 and +1. So what we did with this exercise here by looking at the graphs is it brings us into an idea of what it means for a sequence to converge. And so if we're given a sequence and we evaluate a limit as n approaches infinity for that function and it equals a number, so if it equals a number L, and L could be any finite value, the sequence is said to converge. So if the limit of our explicit formula exists and is finite, the sequence will converge. If it doesn't exist, which means if it oscillates in between two numbers like what we just had, or if it approaches an infinite value, positive or negative infinity, the sequence is said to diverge. So we have a couple of more examples here where we just want to use Desmos and determine if the sequence converges or diverges. And if the sequence converges, let's determine what its limit is. So we're going to use that same link that what we had. Now I actually could do this just by graphing the explicit formula, but since we have this Desmos exercise pulled up, we're going to continue to use it. So we'll go in, we're going to put in this new equation here. We're going to determine if this sequence will converge or not just by looking at its Desmos graph. All right, so we're getting ready to start plotting our sequence. And so I'm going to drag my slider and see, well, what's the behavior of the value of the sequence as I continue to increase my index number for my number of terms. Notice how it gets flat. If I'm graphing a sequence or even a function itself and it's flattening out, it makes it real easy to identify if it's converging because it's getting very close to whatever this number is that I'm looking at. And so we're looking and saying, well, it's getting very close to 3.94-ish to try to figure out, well, what is that actual number that it is getting very, very close to? Well, if I back off of the sequence part, and then actually look at the actual graph of the function itself and say, all right, well, what is the graph itself approaching as I continue to go that way forever? And so what I could do is just look at it in terms of the function value. So if I keep going farther and farther and farther to the right, what am I getting closer and closer to? And I'd say we're getting closer and closer to an output value of 0.4. And so we're going to say here that this sequence converges. And the reason why it converges was because the limit as n approaches infinity of our explicit formula, a of n, was approaching a value of 0.4. So since it is approaching a finite value, we can say it converges. Now let's go look at the next one. We want to look at e to the 2n divided by 2n and figure out if that converges or not. All right, so we get it typed in here in Desmos. We adjust the zoom window so that way we can see. And I'm going to start increasing the size of n. And so it starts off with a very minor increase, and then all of a sudden we start really jumping. And by the time I get to probably the 5th or 6th term, I can't see it anymore on my screen because it has gotten so large. And this sequence here is growing so fast, it's not narrowing in on a number. And we want to know if it converges or not. It is not flattening out or narrowing in on a number, so this sequence diverges. And the reason why it diverges is if I look at the graph of the function itself. So we turn off my sequence graph the actual function here, turn it on, and we're looking and trying to figure out, well, what is happening as I continue to increase the size of n? And it is growing at such a large rate that it is heading towards infinity, so it is not approaching a finite value. So this function diverges. And the reason why it diverges is because what we saw was the limit as n approaches infinity for our explicit function was heading towards positive infinity, which is not a finite value. Therefore, the limit doesn't exist, and the sequence diverges. All right, now let's look at our next one. So -1 to the n power divided by n. And let's see if that sequence will converge or not. All right, and so this one here, as we start to plot, we're going to see something unique happen here because I have -1 to an exponent. It starts off positive, then it goes negative. And then I continue on. It keeps bouncing back and forth. However, as I increase the size of n, notice how it is narrowing in on a term value. As I increase the size of n, I work my way to 100, it is getting closer and closer to that x-axis, which is looking like it's starting to converge in on a certain number. To figure out what that number is, let's look at the actual graph of the equation itself, where if I wanted to try to look at the graph of the equation itself, what you'll notice is Desmos actually won't graph this one, which is pretty interesting. Desmos does have its limitations, so I would have to just look and see, well, what is going on here in terms of the function itself, and so it is getting closer and closer to 0. So what we saw is it does converge because its values are narrowing in on a certain number, so it converges, and we can write that as a limit. So we'd say the limit as n approaches infinity, our explicit formula, is approaching 0, so it approached a finite number of 0, and we saw that it converges. Now let's look at one more. Let's look at -1 to the n power and figure out if that'll converge or not as n increases. All right, so this time I got to plugged in the Desmos, and we're looking at what is happening as I increase the size of n. Well, I'm just going to keep bouncing in between, or bouncing from a value of +1 to -1 as I work my way to the right. So is this converging or not? Well, when I look at the overall behavior of this graph, I got to consider that, well, I'm either being +1 or -1, but I'm not getting any closer to being just one number. I'm stuck at being two different values. So this diverges because it does not approach a singular one finite value as I increase the size of n. So we're going to say this diverges. If we're looking to explain what is going on for our limit as n approaches infinity of our explicit form, a of n does not exist because it is not approaching a singular one finite number. All right, so it brings us to two more parts that are foreshadowing to what's coming up here in a future video. Is it possible for it to have an arithmetic or geometric sequence to converge, since they're two of our special kinds of sequences? Well, think about an arithmetic sequence here. I am constantly adding or subtracting by the same number. And so what has to happen in order for an arithmetic sequence to converge is as I work my way and n increases, I have to be heading towards the same number. The only way that's possible is if I head towards that value, whatever A1 is, meaning that D would have to be equal to 0. So I can have an arithmetic sequence technically. As long as D is equal to 0, then it will converge. And you think about why it'll converge is because you'll have a horizontal line and all of the terms will have the same value. So technically, as n increases, it converges because it stays at that same number. Now, geometrically, what will have to happen in order to converge is that r, the absolute value of r, will have to be less than 1 in order for the geometric sequence to converge. Because what's going to be happening if r is less than 1 is as you'll have an exponential function where you'll be narrowing in, and I'll have exponential decay of some sort as I'm working my way to graph. And if I have exponential decay, I'm going to be narrowing in on some kind of horizontal asymptote.